Hi, welcome to ACTeQ's third Survey Design Express video. Our topic today is seabed geometry options for extreme bathymetry. That's me on the right. My name is Dave Ridyard. My first experience with an ocean bottom cable crew was in about 1984. I don't claim to be a seabed expert, but I'm going to go through some of the issues associated with seabed survey design today. Our topic today is geometry options for extreme bathymetry. We're going to be following this up with a second video which is focused more on the operational issues of designing a crew and analyzing the operation to achieve the most effective operation. Our objectives today are to identify key considerations for seabed design and illustrate how TesserACT can be used to leverage modern technology to deliver cost-effective solutions. I do want to stress though that this is not a survey design course. I'm not competent to do that, but I can ask some of the questions and help you think about some of the issues that have to be addressed. We'll start off by using a simple crossbred model to look at some of the challenges of seabed and also some of the opportunities. We'll look at the impact of bathymetry, mode-converted shear waves, mirror imaging, and we'll also talk briefly about full waveform inversion. And then we're going to put it all together in a realistic project. It isn't a real project, but it's loosely based on the Ormenlange field in Norway. It's going to give us some interesting challenges associated with the topography and the infrastructure, and we're going to start off with an almost conventional design, and then we're going to look at an alternative design using mirror imaging and variable density shots and receivers to try and achieve some significant cost savings. 20 years ago, seabed seismic was all shallow water, and binning on midpoints was okay. But today we're routinely deploying receivers at 1,000, 2,000, even 3,000 meter water depth. And we really have to think about the impact of those source receiver elevation differences. So here's our crossbred model. In fact, we've got two, and it's worth pointing out that we get a different effect if we put the receivers along the contour or we put the source points along the contour. If we ignore bathymetry, the coverage pattern generated by both of these crossbreds is identical. We see a simple square of midpoints halfway between each source and receiver. The purple outline shows how the coverage pattern is changed by applying corrections for bathymetry. Let's think about mode conversion. One of the great benefits of a seabed survey is that we can record mode-converted shear waves. Shear waves are generated when the downgoing P wave energy is partially converted to S wave at the reflection point, and most seabed systems now allow us to record that shear wave energy. P wave and shear wave energy sample different parts of the Earth. Because of the change in velocities, you can see that the shear wave comes up from a reflection point much closer to the receiver. It's a common misconception that PS data is free. It isn't. The most common argument given for this is that the lower velocities require longer records. This may really not be true anymore. With continuous recording, we don't often have discrete records, and secondly, we don't even have to have longer quiet times between shots because we're now able to deblend overlapping records. So the real issue is not the longer record length. The real issue is the minimum offset requirements. You'll see in this exercise, it's much harder to get short offsets when we're trying to record PS data. And this is why. If we look at our crossbred model, you can see that even with a relatively small VP-VS ratio of 2.5, we get a dramatic change in the pattern of sampling on the subsurface. Historically, sea surface multiples have been considered noise. But it's now common practice to treat multiples as additional signal. This additional signal samples a different point on the Earth's surface, so we can use mirror imaging to complement traditional coverage and significantly enhance and infill the traditional coverage. Here we illustrate the pattern of mirror imaging coverage. Notice that it has the opposite sense to the elevation changes that we looked at earlier. With mirror imaging, we're actually sampling a point which is closer to the source rather than being closer to the receiver, as we saw with the deeper elevations. Finally, let's consider the requirements for full waveform inversion. For migration, we all know that we must record sufficient offsets and aperture to capture energy reflected from our target. For full waveform inversion, we need to capture energy from all propagation mechanisms that visit the target. This is well described in Schuster's recent book on seismic inversion. This imposes on us an acquisition requirement that we must record additional offsets, typically up to 4 times the target depth. This leads to a potentially significant increase in data acquisition cost. Let's now look at a semi-realistic project that allows us to look at all these effects together on a single project. It's loosely based on the Ormenlange field in Norway. Ormenlange is an interesting test case for us because it features deep water and steep slopes. Also, all of the production infrastructure is subsea, and this creates a lot of seabed infrastructure that we're going to have to work around. And that's why we've chosen to acquire our survey using ROV deployed nodes. We're going to assume that our objective is to image a number of stacked channel sands, and one of those sands is shown here. You can see that the channel sand that we're trying to image is right below the steepest slopes in the bathymetry. You can see that there are a number of injectors and producers with pipelines feeding back towards the coastline, and we have an exclusion area of 75 meters around each of those pipelines where we're not allowed to place anything on the seabed. We also have a national wildlife preserve off to the east, and we're not allowed to place any receivers in that area either. Our objective is to image the area outlined in blue, and then we will have to extend the survey out based on our requirement for full waveform inversion. And it looks like we need to be extending our survey about 7,500 meters. So that gives us this outline for our receiver pattern. We're using 300-meter line spacing for our receivers, and you can see that we've had to crop the survey to the east because of the wildlife preserve. We've also cropped a couple of lines to the north and south of the survey because we don't want to use these very inefficient short lines. Our shot coverage will extend an additional 3,500 meters so that we can get all the offsets that we need within that area. The receivers have been deployed on a 300-meter grid. We've adjusted the receiver spacing slightly so that we get a true hexagonal geometry with 3 axes, each at 60 degrees to each other. We have 3 vessel passes and 6 shot lines between each line of receivers. That source pattern generates a nice regular 50-meter grid, and again, notice that we've tweaked the spacing on the shots so that again we get this nice hexagonal pattern. You'll see that we've centered the receivers in the middle of one of the equilateral triangles of shots. That's going to give us some very, very regularly sampled common receiver gathers. Now we have to think about how we're going to roll our geometry. With relatively sparse receivers, we can have a wide patch which gives us the full 7,500 meter offset requirement in all directions. Here's a slightly different way to illustrate the roll geometry, where you can see that we have 3 vessel passes flip-flopping between each pair of receiver lines. To help you visualize the roll pattern, I'm going to use TesserACT to create an animation. To accommodate my video capture software, we have to put in a small time delay, and then we select all patches and set the animation running. You can see that we're firing 3 lines of shots in between each of the receiver lines at the center of the patch, and this is how we get our long offset data. Let's think about how we deal with the pipelines in the survey area. I'm going to show the 75-meter exclusion zone, and you can see that a large number of receivers are in the no-go area. Now we need to relocate the receivers that fall within the exclusion zone. And in fact, we've used an algorithm that says that we want to move the minimum distance necessary to get out of the exclusion zone, but we're going to constrain our movement of receivers to be along one of those 3 cardinal axes so that we maintain as much as possible of that geometry. And here you see the impact of applying that algorithm and taking all the receivers out of the exclusion zone. So let's see how well our geometry performs by performing some binning. We're actually going to create 4 binning displays. The first one is going to look at traditional midpoint coverage, then we're going to apply the elevation corrections, and then we're going to look at the mirror image coverage, and finally we're going to look at the mode converted shear wave coverage. This is the traditional fold, and as you'd expect from this very regular geometry, you've got very high fold and very uniform fold over the entire area. When we apply the corrections for elevation, you can see that the coverage moves towards the receiver grid in the center. I'll go back and show you that again. This is the CMP coverage, and then when we apply elevation corrections, it actually compresses the coverage towards the middle where all the receivers are. Mirror imaging looks very much the same, although the opposite effect has occurred. It's actually pushed the coverage out a little bit further towards the sources around the outside edge of the survey. And the PS coverage is by far the most interesting. And one of the things that's really interesting here is that PS coverage is very sensitive to elevation differences. And you can see the imprint of the bathymetry on this fold map here quite clearly. For our full waveform inversion, we'd said that we wanted to have offsets of at least 7,500 meters in each bin, and you can see that this geometry has exceeded that. The minimum offsets are a little bit more interesting. You can see the natural pattern of the receiver layout, but if we zoom in and look a little bit more closely at the area around our gathering station, you can see that we do have some holes in the coverage for minimum offsets. And perhaps with hindsight, we should have added one more receiver in here to fill in this hole in the short offsets. The PS coverage is even more dramatic. And of course, the problem here is that because the reflection point has moved closer to the receiver, in order to fill the bins halfway between two receivers, we have to take coverage from shot points which are much further away, giving us a much worse offset distribution. So if we were really going to acquire and process this PS data, we may have to dramatically change this design to capture better short offsets. Well, I'm quite happy with that design. Unfortunately, management is not happy. As you can see, our accountants are complaining that this survey is going to cost us over $20 million, and we're going to have to look at some cheaper alternatives. So what we're going to do is we're going to look at some variable density options. The green boundary is the area where we're going to maintain the very dense coverage throughout that area. But when we get outside the green boundary, we're going to reduce the receiver density to a 400 meter grid. And when we get into the shot area, where we only have shots, we're going to reduce the density of the shots. You can see our 300 meter receiver spacing inside the green area, going to 400 meter spacing between the green area and the blue boundary. Notice that we do have a few idiosyncrasies that occur at the interface between the two. And while doing this project, I realized there are probably some smarter ways to do this, but this illustrates the point that we're going to use variable receiver spacing. Our source geometry needs a little explanation. If we use a conventional flip-flop geometry, we end up with this irregular pattern where we have pairs of lines 50 meters apart and then a 150 meter gap. And that's very irregular, and we don't want to do that. So we've come up with a slightly different scheme. We're going to use what I call an interleave flip-flop configuration. In this case, we use 100 meter source separation instead of 50 meter source separation, and we interleave the lines. This way, when we terminate the odd numbered lines, or the yellow lines in this illustration, we're left with a regular 100 meter shot grid outside our dense area. And you can see that illustrated here, that we've got 50 meter grid inside the dense area, and we've got a 50 by 100 meter grid outside the area. The justification for lowering the source and receiver density at the outer edges of the survey is that we're really only using long offset traces with relatively low frequency content. So with these long offset traces, it's acceptable for us to have slightly lower spatial sampling. And you can see that our maximum offset is just what we want it to be in the area of interest and even in the secondary area of interest. At the outer edges, you can see that there is some impact of our sparse source line spacing. But I would argue that if we were to do Fresnel zone binning or even overlapping binning, that's really not going to cause us a problem. I think these days we can probably interpolate those missing long offset traces given the density of the grid that we have here. When we look at the minimum offsets, now you really see the impact of changing the density from 300 meters to 400 meters. Again, I think this is probably acceptable in this northwestern area of the survey where we're in relatively deep water. This may not be acceptable in the eastern area where we're on the continental shelf and we have much shallower water. As you would expect, the conventional fold corrected for elevations with this geometry is very good, and you see that we still have high fold inside our area of interest. In the shoulder area between the green boundary and the outer blue boundary, you can see that the fold is dropping off, and this is where I think it might be useful for us to consider the mirror imaging coverage. If we can combine this mirror imaging coverage with our conventional coverage, I think you'll see that we're actually going to have a high fold, well sampled survey. And we've accomplished this while reducing the time to acquire the survey by over 30%. So that's almost the end of today's video. I do want to mention our next video, which is going to be covering operational analysis, and we're going to be talking about how we balance methods, vessels, and equipment for maximum operational efficiency. We'll look at simultaneous source, And we may also look at a couple of other technical issues such as compressive sensing, Fresnel zone binning, and the impact of velocity models in terms of modeling curved rays as we look at the coverage. In summary, survey design is all about balance. We have to accept the constraints of safety and environmental impact, and then we have to trade off time and cost against imaging performance. New technologies like seabed nodes, mirror imaging, and simultaneous source really open up tremendous opportunities for us to create high-quality imaging at much lower cost than we could in the past. Well, I hope you've enjoyed our third Survey Design Express video, and I look forward to seeing you next time. Thank you very much. Bye-bye.